Hello there, it's Paul with a very short Math156 video about normal density functions and their moment generating functions. This is not really a very important application of R. I wrote it mainly just to satisfy my own curiosity and to convince myself that R agreed with the results that are proved in the proofs of the week for the second week. So here goes. Let's begin by looking at some graphs of the normal distribution. Here's the so-called standard normal distribution. I didn't specify either the expectation or the standard deviation, so they default to mean of 0, standard deviation of 1. And of course I can't plot this from minus infinity to infinity. Minus 5 to 5 pretty much shows the central peak nicely. If I specify a second argument of 2, that overrides the default expectation, and I get the normal distribution with a mean of 2. You can see the density function is shifted 2 units to the right. Do it with minus 1. I get one where the mean and the peak are both at x equals minus 1. Now let's look at the effect of different variances. Here's the standard normal distribution again. Now I'm going to overlay on that one where the standard deviation is the square root of 2, so the variance is 2. Notice with all of these I'm using add equals t so that I overlay a graph on the original graph in a different color so we can tell which is which. And you can see that is spread out more widely, and because the area under the curve has to be 1, a greater spread implies a lower central peak. Here is the same thing, only now what I have done is to specify still a mean of 0, but a standard deviation of 2, a variance of 4. It's sometimes hard to remember that the third parameter is the standard deviation, not the variance. Now let's look at the moment generating functions. I don't know how I ever figured out how to do this. It must have taken me half an hour in order to get these functions working correctly, and do not feel responsible for the details. If you ever need to do something like this, probably the best thing to do is open this script, copy these 3 lines, and modify them. So first I've defined the density function. It's a function of x and y because what I want to do is take the normal distribution's density function and then multiply by e to the xy. That's what we have to integrate in order to get the moment generating function. And what I found when I just wrote this directly as a function was that I couldn't pass it as an argument to integrate, so I finally discovered Vectorized Args, and when I set that equal to the character x, that means that this can be applied to a vector and it will produce a vector in the normal R manner. Then to get the moment generating function for the normal distribution with mean 0 and variance 1, MGF N01, I have to create a function of x, and I do this by applying using sapply, and a function of y that I get by integrating the density function from minus 20 to plus 20. That's effectively minus infinity to infinity, and the y equals y at the end says the thing we're integrating over, since density is a function of 2 variables, is y, and the $val means I get just the value and not all this business about the expected error. Okay. So I've graphed that function in the next line, and there it is. Hey, that looks like a parabola, doesn't it? And that's exactly what I proved in one of the proofs for week 2. And to confirm that it's exactly right, that is, that I get e to the x squared over 2, I graph in a different color that function. I overlay it. If one curve obliterates the other, then the two functions I'm graphing are the same. This has become my standard technique for showing that two functions are equal when using R. Now suppose we do it for the normal distribution with a mean of 1 and a standard deviation of 2. Once I figured out how to write this code, I just copy it and modify it. So here's the moment generating function for n1, 2. And you can see that's a piece of a parabola too, but it's a different looking parabola. So somehow the mean and the standard deviation have got encoded in the shape of that parabola. Theoretically, this is proved in the math notes. In this case, the moment generating function should be x plus x squared, and sure enough, when I graph that, it lies right on top of the original curve. So what the moment generating function does is to take the mean and the standard deviation of this normal distribution and to encode it in parameters of the parabola, where the lowest point in the parabola is and how sharp or spread out it is. And in fact, that information is closely connected with the first and second derivatives. Rather than trying to use the R function that takes derivatives, I'm just taking two values that are close together, one at h and one at 0, dividing by h. I'm not passing to the limit, but the value of h I used is small enough that I might as well have. And you can see down below I get 1.0015. That's the expectation. That worked out pretty well. And if I take the second derivative, which I can do approximately by taking the value at h plus the value at minus h, subtracting twice the value at 0, and dividing by h squared, I get the second moment. And when I take the second moment minus the square of the first moment, there's my variance, which indeed came out very close to 2. Now the really important result is that if you add together independent random variables, you multiply their moment generating functions. So if I add together 3 independent random variables with a mean of 1 and a standard deviation of 2, I should get a mean of 3 and a standard deviation of 6. So there is the cube of the moment generating function. And I've been a little bit sloppy. I guess I should have said n1 square root of 2 and n square root of, I can never remember. Anyway, I know I need the standard deviation here, which is why I use the square root of 6 and my otherwise standard code. And when I graph that, it's exactly the same. This proves absolutely nothing, but it shows that in at least one specific case, this general principle that adding together independent random variables is equivalent to multiplying their moment generating functions. And that's all I have to say on this subject.